Hello, I'm Joel Stanley. Thanks for joining us today. I'm going to talk a bit today about QEMU and OpenBMC and how we use it in the project, and hopefully how you can use it in the project in the future to help your development and testing, and make a high quality BMC code base. So who am I? I'm a free and open source software developer from Adelaide, Australia. I'm a long distance runner. I enjoy going out for 50-kilometer runs on the weekend. I thought I'd include that especially for our Indian audience. I'm a cricket fan, an Adelaide Oval member. I don't have an IPL team, but I love going to test matches every summer. Hopefully COVID slows down and we can all go to cricket this summer. I've been working on OpenBMC at IBM since 2015, which is when IBM kind of started working on OpenBMC. If you know a bit about the history, IBM had its own OpenBMC code base that was distinct from the Facebook one that we worked on for a while before joining forces a couple of years later. And my role when I very first started working on OpenBMC was to get Linux into shape. So we worked on doing an upstream Linux kernel port and upstreaming U-boot changes. The Linux port's gone really well. The U-boot hasn't had as much love over the years, but it's been going okay. And as part of the work that I do, I'm also the ASP kernel maintainer for Upstream. So I kind of have dual hats in that I maintain the OpenBMC Linux kernel tree, and I maintain the Upstream ASP tree and all the drivers that are involved there. So we're here today to talk about QEMU, and I guess I can't ask you to raise your hands, but hopefully people here have heard of QEMU. If you haven't, a little bit of background. It's got two main use cases. That's virtualization, so you're using it for the KVM infrastructure under Linux, and the other one is emulation. There's two types of emulation. One is called user emulation. That's where QEMU can dynamically translate binaries to run on your Linux system. So if you've got an ARM binary, you can run it on your laptop, your x86 laptop. We're not talking about that today though. We're here to talk about system emulation. So that's where you're emulating the full computer that, in this case, that the BMC is running on. So we have an ARM CPU. We have a bunch of system on chip peripherals. I've got external devices that sit outside of that system on chip, and they're connected via all kinds of buses like I2C and Ethernet, and FSI and LPC, eMMC, SPI. So that's kind of in a nutshell what QEMU is. It's an application that lets you run other bits of code on top of your computer, and that can be really handy as we're going to find out. Now my slides are being weird. All right, so I'm going to try and do a demo. One of the delays starting today was that everything went weird as far as my computer went. So just bear with me a little bit. So there's multiple ways to, is someone talking? I'm hearing beeps. There's multiple ways to use QEMU. We can, depending on what we're trying to test. So the kind of simplest way is if you've got a full system image and you're trying to run that. And so I can cut and paste this. Looking in the chat, is that the beeps that I'm hearing in the background? No, okay. So this command is telling us, can people see that? This command is asking QEMU to start a machine called Romulus BMC. That's one of the open power platforms that OpenBMC supports. We're going to have a network setup that uses user space networking. So we're not going to set up full proper routing of packets out to the LAN that my laptop's on. It's just going to be an emulated network that runs in user space. We don't want the GUI. We're just going to run in the terminal window, and we're going to boot a drive with a backing file called /Romulus. So /Romulus is in this directory, and it's the NTD interface, so it's an SPI NOR device, and the backing file is a raw file. There's other types of files we can have. So if I run that, it starts executing from the side of Flash, and so we run QEMU. QEMU then loads the fit from Flash. That then does its thing, and we jump into the kernel. Okay, so now we're running the kernel, and the kernel will boot, and that'll go through and come up to user space, and then we'll be running OpenBMC user space, just the same as if I'd gone to the hassle of flashing that onto an actual machine. So there we can see OpenBMC. That's one way to run it. That's really useful if you've got a full system image that you've built and you're trying to inspect something inside of it, or you want to copy an application in it and test your new application. I'm a kernel developer though, so lots of the development I do involves building a kernel and testing that against the hardware or the virtualized hardware. So what I will do is go into my OpenBMC kernel development tree, and I'm going to boot this. So this is similar to the command we ran before. We are going to, oops, that's not what I want. It's actually got a lot of stuff we don't need. Let's make it look like it did before. All right, so we're going to boot a Romulus machine again. So let's boot a 2600. The Tacoma is a 2600 OpenBOW development board. We're going to run it with the same options, except now instead of pointing at the Romulus device tree, I'm going to point it at Tacoma. And unlike before where I pointed it at a full system image, we're going to point it at a little init RD. And this is a little init RD that I have there for testing. Instead of a full OpenBMC user space, it's just got a tiny little user space that we can use to make sure that the kernel gets user space, and we can run that. So off it goes, hopefully. That's embarrassing. All right. All right, let's not do that demo. That's okay. Normally that would work because I do that all the time in my day job. So that's directly booting the kernel. So the big difference there is we don't go through U-boot. We load the kernel straight to RAM and run it from there. So it's not quite the same boot process, and you can't test quite the same things. But for lots of use cases like developing kernel drivers, that's a really good way to test your kernel changes and debug them. The other way that we can use QEMU is to some people are building systems that use an SD card or an eMMC device as the root file system, and QEMU has support for that. So here we're pointing, instead of pointing at a NTD device like we did with Romulus, we're pointing at a SD device and booting that one. I won't try and do that because the demo gods are not loving it today. Right, so there's a couple of use cases that I'm going to walk us through today to kind of give you a feel for what QEMU can be used for and hopefully help you use it at home. If you want to follow along, I was hoping to have a Docker image published, but it didn't quite get there. If you want to go to Go to github.com, Shinky, QEMU, OpenBMC, QEMU tutorial. Here there's a Docker file and a build script. You can run the build script, which just downloads a couple of images from OpenBMC CI, and then build the Docker file. And that will give you a Docker image that you can paste the commands that I've got in my slides into and go through and kind of follow along and experiment for yourself. There's no need to do that today, but that might help if you're trying to follow along later on and get an understanding for this. Ultimately, it'd be easier if you have all the tools installed on your development machine, but the Docker image is a nice little way to play around with the concepts without having to do all that setup work. Right, so building a custom kernel. That's crazy. The development workflow that I have when I do my job as kernel maintainer, I build a QEMU, I build a kernel, and then I point QEMU at it, and I boot it. And if I've just written a bug, if I've written a null pointer dereference or something, it'll crash really quickly. And I'll be able to see that quite quickly without having to wait for the full cycle where I might flash a real bit of hardware and then reset it and get in there and boot it, or try and get it net booting working or whatever. So let's run these Docker commands that I've got here. So can people see my terminal? Can someone speak up?
Yes, we can see it.
Excellent. So we're going to run the Docker container, and so inside here I've pre-installed the toolchain and QEMU from Debian. So this is Upstream QEMU. It doesn't have any customizations or any other tree patches. Most of the work that we've done, actually, I skipped a slide. Let's go back to. I missed. This is the other side of my QEMU and OpenBMC slides. I just realized I'm only seeing every second slide in that display. So just jumping back a little bit, QEMU in OpenBMC. So we spoke about what QEMU was and what it could do. QEMU in OpenBMC, there's a bunch of us at IBM that have kind of as a side project, a 20% project, whatever you want to call it, we've created an A-speed model in QEMU. And so what that does is the 2400, 2500, and 2600 is implemented. And so it can run the ARM core, so run the instructions that those three system on chips have, as well as the inbuilt peripherals that are inside the SOC. So things like networking and I2C and all the storage devices have models in them. And so we can test our code inside QEMU using that. It's been kind of a bit demand driven. So as kernel developers, we want to write certain drivers and test certain things. And so they're the parts of the system that have gotten attention and have been implemented. As we go through this talk and you identify areas that haven't been modeled, I encourage you to get in there and get some models written so that it can be more useful for you. One of the things that my team prides itself on is getting our code upstream. So most of the changes we've made have trickled upstream. There's a few other tree patches that are works in progress, and we do a bit of staging in Cedric's tree. But most of the code that Andrew, Cedric, Jeremy, Rashmika, and myself have written has all gone upstream. So if you're running Debian unstable, you can apt-get install QEMU system ARM, and you'll get QEMU 5.1, and it has all these changes in it. You don't need to build it yourself. And so, as I said, we can boot full OpenBMC systems images. And the other big use for it, aside from kernel developers, is it's used in OpenBMC continuous integration. So whenever you submit a patch to Jenkins, to Gerrit, it gets built as part of the Jenkins setup. And Jenkins will run it on one of the machines. It currently just runs it on the Romulus machine. But if someone was to volunteer some time and some compute resource, we could run it on more machines, more emulated machines, that is, as part of CI. And the advantage of doing that is that we don't just have build time testing, we've got some kind of boot time testing. So the kind of bugs that only show up when you run the code can be detected. All right, sorry to jump back. Back to our building a custom kernel workflow. So we're in Docker here. The Docker image also has a clone of the OpenBMC Linux kernel tree. Just the shallow clone, so there's only one commit there. And so in here we can make the def config for the A-speed machine. So this will build, it's called G5 def config. This will boot on the 25 and 2600 machines. And then we can build the kernel. This is going to go through and build an OpenBMC kernel. The first build obviously takes a bit longer, and then if you're doing incremental changes, it'll be a lot quicker. While we're talking about that, I'll load up. While that's running, does anyone who's listening have any questions? Feel free to, or can they take themselves off mute, say? Or do you have to do it?
Yeah, there's no chat questions. So if anybody has questions, please speak up.
I have a question, like if I apply patches to the kernel, how I can do this, because it looks like a Docker all are integrated everything. So can you show this kernel source code tree and how I can apply the patches in this?
Sorry, your audio was really scratchy. Did anyone else catch what that was?
I mean,
so his question was, how can he apply a patch while he's building the kernel? So just show us a path.
That's a different tutorial, I think. I can run that tutorial another day, but yeah, there's a couple of ways to do it. I tend to use the bare kernel tree without building the kernel as part of Yocto. So there's kind of two ways to do it. There's to do it inside Yocto, where you can use DevTool modify the same way you'd modify any other application that's been packaged as part of Bitbake. Or you can do it the way that I do it, and that's you clean the kernel tree and edit the code in the same way you edit any code tree, and then rebuild it. And kind of these instructions that we're going through today will show you how to do that. So essentially, doing the make def config, and then make will produce us a kernel that we can boot in QEMU. There's a few more steps involved to get that to the point where we can boot it on hardware, and that's kind of out of scope for today. But feel free to follow up with me on the mailing list, and I can write out some instructions. There's a fair few kind of instructions out there on the wiki and whatnot. I can probably point you at something that's already there. But no, that's a good question.
Yeah, we also use DevTool modify and build like that. But here I don't see the kernel source in which path it is there, so that I can build that. I mean, most part of that DevTool modify, applying the patch and building that thing, we do that. But I don't know how we have to do differently for this Docker environment and with QEMU.
Right, I think your question was you're not sure how to then test it in QEMU, and so that's what we're going to go through in a sec. Unfortunately, I had to rebuild this because I had to reboot my computer just before the talk started. But once it's done, which will take about another minute, we can kind of go through that and show you how to boot it in QEMU, and we're also going to learn how to debug it inside QEMU, which is another important. Were there any other questions while we're waiting?
Joel, a quick question here. As you set up your Docker environment, does it set up for your cross-compiling tool also?
Yeah, so let's have a quick look at the Docker file. I had to teach myself how Docker worked again today, so we can learn together. So this is the Docker file I wrote. What we've got here is, whoa, my computer is really laggy. We're using Debian Unstable as the base image. The reason we picked Debian Unstable is because it has the cross-compilers package and also has the latest QEMU package. And then these are the files that the script that you run first downloads. So it downloads the OpenBMC Linux source tree. It downloads a binary from CI, from the continuous integration system of Romulus. It downloads an IRD for Romulus, and there's a GDB init file that is just for convenience sake that's in this repository as well. We then use apt to install the compilers, and so this is the important one, the cross compiler for ARM. We can use, it doesn't matter that there's hard float variants and non-hard float variants. It doesn't matter for the sake of building the kernel which variant we use. That's only about building user space programs. GDB multi-apps, this is the GDB that can debug ARM programs. And then the rest of these are dependencies of building the kernel. We've also got QEMU system ARM, so that's the QEMU system emulator package for this distro. And yeah, again, a bunch of tools for building the kernel. So that installs the tools. The other important steps are we set the environment Arch to ARM because we're cross-compiling for an ARM kernel, and we set the cross-compile variable to ARM Linux GNU ABI. So that's the prefix for the tool chain. So it's going to ARM Linux GNU ABI -GCC would be the C compiler. And then the work directory is /build. So that's what the Docker script's doing. You should probably always have a look at a Docker script before you run it on your laptop. Make sure it's not doing something bad. And so that's how that works there. And this was the download steps. Sorry?
And what is the base OS you need, like Ubuntu, any specific version?
Anything that'll run Docker containers. So yeah, I mean, I use Debian on my laptop, but whatever you have in a VM or on your machine, anything that can run Docker containers. I guess in theory you could do it on the Windows or OS X, run containers on those. All right, I think we're almost built. Maybe not. Want any more questions while we wait? No, that's okay.
Do we support a SM bus I2C interfaces also in the QEMU?
Which I2C, yeah, that's correct. What was that your question?
Probably I type. Wait.
Sorry, can you just say that one more time?
I think he's going to type it on the chat session.
Oh, excellent.
So the
Thanks.
question, the question was, how do we support the SM bus and the I2C communication buses with the QEMU?
Oh, yeah. So we have a model of the I2C master that allows us to attach slaves to it. So emulated slaves. So in the context of the machines we have, we've attached some example slaves like temperature sensors. So there's a couple of temperature sensors that are modeled. That's something actually I'll talk at the end of the talk about how to write new models for I2C devices. It's relatively straightforward, especially if you've got a nice example to copy, of which there's a whole bunch in the tree, to add new models for devices. All right, so sorry for the delay. Here we are. we've built Linux. It's ready. Now we can cut and paste this command here, which is going to boot all right, so we're going to, let me read through it. So we're going to boot Romulus with a kernel, this image, with this device tree, and this in the RD. So it's the proper OpenBMC in the RD. And we've got a Flash file called Flash Romulus. Oh, whoa. It crashed. Huh. I tested this just before. All right, that's really annoying. Huh. I can see the bug. Feel free to interject. All right, so we can see there what it looks like when something crashes inside QEMU. That will keep rebooting because that's the way the OpenBMC kernel is configured to restart when it crashes. I can exit the QEMU session by pressing Control A and then X, and that terminates QEMU. So I have a bug. Yeah, we do have a bug. Here's how you might debug the bug that you have in your QEMU instance. So as you can see there, it's panicking, it's oopsing at a certain point in the boot process. So I'm going to open up a second terminal window, and we're going to do a bit of debugging. So QEMU has a GDB server built in. By passing the argument -s, it will start a GDB server that listens by default on localhost port 1234. And so if we add that to our QEMU command line, we'll be able to connect to it with GDB. The other thing we can do is start QEMU with --S, and that tells QEMU, don't start running, just load everything up and get ready. And essentially it holds the CPU and reset for us to tell it to start. And we can use the QEMU monitor, or we can use GDB to tell it to continue. So I'm in my Docker container here already. I'm going to tell it to start. So we're debugging the kernel that I just built. And you can see here, it prints a warning. You can just ignore that one. And it stopped. It's not doing anything. So I can open a second session into that Docker, running a Docker container. Except I changed the instructions. Oh, this is not going well. All right. It's going to have. Again. Actually, I'm not going to do this inside Docker because everything's gone bad. But we can still do the demo to see how I do it on my system without using QEMU. So here we're going to load up a very similar command, but it's just using my build tree for the kernel. And so we'll load that with -s. And so the other command we're going to run here is GDB. So GDB multi-arch is a GDB binary that supports pretty much all of the architectures that binutils supports, which includes ARM. And we're going to tell it to load the VM Linux from my development tree. And then EX means this command as soon as you start. And so it's going to execute the command target remote localhost 1234. And so remember from before, by passing -s, which GDB server is going to listen on localhost port 1234. So if we do that, we're now connected to the GDB server. And so it's read in the VM Linux. So that's the kernel image with all the debugging symbols inside of it. And it didn't work. The demo gods are not smiling on me today.
Are the quotes a single quote?
Keyboard map is wrong. All right, I'm just going to type it out. Remote localhost. All right, so here we are. We're at the start of RAM. So due to the way QEMU models booting the kernel directly, it starts executing from the start of RAM instead of from 0, which is instead of flash, so that's okay. And so we can type C for continue. And in the top window, after the kernel decompresses, we should see the kernel booting, except we're not. I guess we are. Here we go. So off it goes. If we kind of scroll back up, we can see the normal boot process of the kernel. It's sitting there and it's recognized it's running on this BMC machine. It's reserving some memory. It's doing all the kernel-y things. It loaded the init ramifest that I had there. It's loading lots of the BMC drivers and RTC master. We've got an emulated RTC real-time clock on the I2C bus. So it's gone and read the current system time from that in UTC. And then off we go, and we're in user space. Okay, so as far as debugging goes, we don't have the crash anymore, which is good, but we can still inspect the kernel as it runs. So down in the bottom window, in the GDB window, I press Control-C, and that's halted execution of QEMU. And we can use BT, which is shorthand for backtrace, to see where we are in the kernel execution. And so here we are with the call stack goes from start kernel all the way up to the idle loop. So we're currently in kernel space, executing the idle loop, waiting for something to happen, waiting for some code to be scheduled. We can put breakpoints on various points of the kernel. The IRQ line for FEC. And so I ran I2C detect, which caused some I2C traffic, and the IRQ handler for the I2C bus just fired. And so we can, it's a bit noisy, but we can see there the IRQ code's executed. We're in the A-speed driver, IRQ A-speed I2C, and then that calls through the IRQ chip infrastructure into, it's currently executing a spin lock, but that's running inside the A-speed driver at that point. So we can the local variables and the registers and do all the things that we do when we use GDB, and then C for we can delete the breakpoints and D for continue, and off it'll go. So that's a bit how to use GDB. And if we quit out of GDB, the system keeps on running, and so we're still running the ARM up there. So that's a little bit how to use GDB to connect to QEMU to see what's going on. Right. Do we have any questions on that one? No? Excellent.
So I saw some NCSI message in your kernel, and so does that QEMU support the NCSI?
It does. It's a very simple model of NCSI. And in fact, I'm not sure if all the NCSI emulation is upstream. We might have to use the OpenBMC QEMU tree for better support there. But yeah, it has some basic support. It's enough so that NCSI networking works under QEMU. But if you were trying to test NCSI, then we'd probably want a bit more support added to QEMU to be able to do a bit more testing of that.
Okay, thanks.
That's a great question though. And you see when you're on QEMU, it prints the message, I think it's like 8 times about NCSI not working. Whereas when you do that on hardware, it only prints it once. If you'd like to get in there and fix that bug, I would be internally grateful. I'll buy you a beverage of your choice at the next OpenBMC face-to-face. It's done that since we started. So, all right, so that was the kind of the first use case that we had, and so that was very focused on kernel development and kind of what my day-to-day job is. But I realized that the majority of us work on the user space components of OpenBMC, and so we'll talk a little bit about how to do that. I spent lots of time making sure it'll work inside Docker, and my Docker is misbehaving today, so I'm not going to try it in Docker, but the instructions are in the slides, and I will go back and work out what that bug was and update the Docker image if need be to not have that bug. So sorry about that. So if we go QEMU system and we'll build up the command together. So we're going to run Romulus again. And we're going to run with networking. And this time we're going to add a port forward. So QEMU runs this user space networking stack, which can be useful for a bunch of things. You can TFTP from your host machine into QEMU, but you can also forward ports. And so this host forward, SWD directive, let's just say, let's forward port quad 2 to port 22 inside the guest. Port 22 is the SSH port. And then instead of booting my kernel image, I'm just going to boot a Romulus full flash image. Because the goal here is to test run our own code inside the QEMU image, not so much to test the kernel. So we can see U-boot going past there. Now that's booting. And into OpenBMC user space we go. So what we're doing here is useful if you say do development using the SDK. You might build your application using the Octo SDK. You might build your application, have the binary there, and maybe your normal workflow is to copy that binary onto a running BMC system somewhere in your lab. By using QEMU, we can instead run that on the emulated machine on our laptops, which has some advantages. It's sometimes easier to debug. Sometimes it's easier to get access to. because as long as your developers have a laptop, they can do this. And for some applications, there's no real difference running it inside QEMU versus running on some hardware. That really depends on what the interactions are. Obviously, if your application is interacting heavily with the host, then it's a bit harder to test on QEMU.
So can I also transfer the image in QEMU like we do in the hardware?
Can you run the same image?
No,
yeah.
Can I transfer the application, as you just mentioned about the application binary, right?
Yeah.
So can I SCP application binary?
Generally, yeah. I mean, I guess it depends on all the dependencies your application has and whatnot, but definitely whenever I've done some user space work on OpenBMC, I copy the executable across and load it in. All right, here we are. We are almost at user space. Log in using the top secret password. All right, so here we are, running Romulus machine. So my tutorial had this wonderful little one-liner. That's not pasting correctly. So let's edit it in a text editor instead. Okay, so the world's worst C program. My keyboard mapping's wrong. I've become a European. I can't type. Oh no. That's embarrassing. All right, so here's a horribly written C program. We're going to compile it using a cross compiler, and we get lots of warnings because it's horribly written, but that's okay. And so now we're going to SCP to port quad 2 below. Root at localhost. So localhost being my laptop, but port quad 2, remember, is being forwarded into QEMU on my laptop. So I've done that before. Ignoring the fingerprint errors, we can log in using the top secret OpenBMC password. All right, so now we've SCP'd hello into QEMU, and look, there it is. Excellent. And I can execute it. Hello, OpenBMC. Okay, so now we've shown that we can build our application. Normally, we might use the OpenBMC SDK, and obviously it'll be a much better written program than my horrible C program, but we can copy that into our QEMU image and execute it. And hopefully that allows us to do a faster test debug cycle by using QEMU. So that's the end of the second use case. On to the third use case. This one, I'm not sure how the x86 and the ARM OpenBMC-based systems work, but in OpenPower land, we have this concept of pgood. And so that's a signal that comes into the BMC via GPO that tells the BMC that the system is ready for the host CPU to be powered on. You know, all the regulators are stable and all the power supplies and whatever are doing their thing. There's been no faults detected. You know, the fans are present and we're ready to send power to the host processor. So as I said, this is the GPO input to the A speed. But because we are running under QEMU, we have control over all the GPOs, so we can change the state of them. So we've got our booted QEMU in front of me here, running an ARM machine, so just proving that's QEMU. So we can drop to what's called the QEMU monitor. So the monitor is kind of the admin panel for QEMU, and it lets us inspect the state of QEMU. We can dump memory and attach virtual devices and detach virtual devices and manipulate the state of some of them. So I'm going to drop to the monitor by pressing Control A and then C on my keyboard. And so now you can see here we're in the QEMU monitor. It has an inbuilt help that is a bit terse to read. I recommend jumping on the QEMU online documentation to learn a bit more how to read it. But we can, we can print things like the whatever that register is inside the SCU, the strapping register, I think that is. So we can sit there and print, that side of the hardware and verify that our code's doing what we want to. But in this case, we're going to try and test pgood by using the QEMU monitor. So I'll switch back to QEMU proper, to the emulated machine. And so on an open power machine, we type OpenBMC util power, and that will query the state of the pgood GPIO. And so here we go, pgood is 0, pgood is low. So we're not ready. The system is not ready to turn on the host. But we want to test our applications as though the host was ready to be turned on. So how do we do that? We go back to the monitor and we can look at the help for, so I've taken screenshots of the help for QOM get and QOM set. So QOM is the QEMU object model. I made up the pronunciation, so I've probably got it wrong. And we can manipulate properties of objects. So state inside QEMU using these APIs. I'm not an expert in this area. And so if we want to learn more together about this, then we should talk to some of our experts that we have in the QEMU community and also in the OpenBMC community. But I know enough to be dangerous. I know enough to play around with this stuff. So QOM get. So I know that in Romulus, GPIO D2 is the GPIO that's used for pgood. So I can do QOM, get rid of this one. QOM get GPIO, because we're talking the GPIO model, and the GPIO name is D2. Okay, it's false. As we saw in user space, we saw when we asked what the state it was 0. So now we can do QOM get set. GPIO D2, we're going to set it to true. And we can repeat the get command and say, okay, now it's true, excellent. Control A, C gets us back to user space. Now we can ask OpenBMC power what it thinks pgood is, and it's 1, excellent. So there we go, we've used the QEMU monitor to manipulate the state of the emulated machine to test our software. And so obviously this is a pretty basic test, just flicking a GPIO. QEMU can also be used to do more advanced manipulations. You can use it to set temperatures inside I2C temperature sensors, for instance. And so you might be able to use that to test your fan control algorithms are doing the right thing when the system temperature gets too high, and advanced things like this. As far as I'm aware, there's no one in the OpenBMC community that has that kind of testing in place yet, but that would definitely be a way to kind of increase the quality of your code and the ability to refactor by having some automated testing that went through and tested that your applications are all working in synchronization and whatnot. So that's pgood. Any questions there? No.
Hi, is this QM set? Hello.
Yeah, hello? Sorry, what was that one?
Yeah,
I can hear you.
Yeah, hi. Is this QM set will work even if the particular GPIO is associated with another daemon? Or?
Yeah. So
like, say for example,
Oh yeah. Continue your question. Sorry.
Yeah, that's what. Yeah, please proceed.
Yeah. So because we're manipulating the hardware, it's as though I had a server, sitting in front of me, and I just, tied a GPIO to the rail. So I'm changing it independent of the state of all the software in the system. The software is then going to react to that. So if you say had an application that was tied to an interrupt handler, you would see the interrupt handler fire inside the BMC kernel, and then that would cause user space to do its thing, and you'd have the flow-on effects there. Does that answer your question?
Yeah. Yes. Yeah. Thanks.
Cool.
So does this mean that it's a hardwired changing? So the QEMU will trigger the GPIO if any application is monitoring the GPIO, will get the trigger?
Exactly. Yep.
Okay.
Awesome.
I have another question. So you have enabled user network, right? So is there an option to have a network with the kernel support? So can I set the IP and the same IP can be pinged from the host?
So networking in QEMU is complicated. The user stack is the easiest way to use it. But yeah, if you want to do more advanced things, say you want to connect a bunch of virtual BMCs together, or you want to have your BMC talk to other devices on the network, you can set up a bridge on your host Linux system, the same way that libvirt would do if you're running like a KVM guest. So if you're using KVM to run a guest on your Linux system, you would use libvirt to create a bridge interface and then connect your guest to the bridge interface, and it would have routable networking onto your local area network if you choose to enable that. So you can do the same thing with QEMU in this case. That's just a little bit more complicated. Cedric is the person to talk to about that. So send mail to the list if you can't get it working from the QEMU documentation. I've got links at the end of the slides to a bunch of different documentation. So if you can't work that out from there, then have a look there. But yeah, that's a good question.
Yeah, thank you.
Joey, I have a question. Is it possible to attach an I2C device when the QEMU is running using the QEMU API?
Excellent question. I've got no idea.
Okay.
I would assume yes. And if it's not possible out of the box, it's something that we could add. I know that you can dynamically attach USB devices. So I would not be surprised if you could dynamically attach I2C devices. But yeah, I've not tried that myself, Lee.
Okay.
Cool, good questions. I might move on though. So those were the three scenarios that I'd kind of put together to help talk about some of the features of QEMU. Hopefully everyone's got a little bit of an appreciation for how QEMU could help them in their development, and also for, I think we might already have some ideas for new models to write to be able to test systems, which would be really cool to see. And so on the topic of new models, how do you start developing QEMU? Well, I'm glad you asked. I put this slide together. QEMU is written in C. It's a bit of an interesting looking dialect of C. It uses preprocessor macros very heavily, and it's a bit hard to navigate when you first start. But as a general rule, there's always something to copy inside QEMU that gives you a good starting point for developing your code. So as long as you pick the right thing to copy, it's usually pretty easy. The QEMU project has had a bit of an injection of activity that I've noticed over the last 12 months or so, where lots of refactoring's been going on and lots of kind of code improvement. They recently changed their build system, which is a polarizing thing to do, but they've changed over from auto tools. So there's lots of stuff going on there. So the development model is also similar to Linux kernel in that they use Git for version control, mailing list based code review, and to get your code in the tree, the maintainer for that subsystem will send a pull request. So anyone who's submitted a patch upstream to Linux is very similar. But one thing about QEMU is it's a much smaller group of developers working on it. So in some ways, it's a little bit less intimidating than working on Linux kernel, just because there's not a cast of thousands that are out there, and it's a little bit easier to understand who you should talk to about a certain problem and who's going to be able to help you with your problem and review your code. So when you write a model in QEMU land, aside from all the QEMU boilerplate that you need to write to register your driver. The basics are implementing a read and a write callback for when the system tries to address the address space that's associated with your hardware. So if you're modeling a bit of internal ASPEED IP, say like the I2C master, when that's actually a horrible example. Let's say you're modeling the ASPEED timer. So that's a bit of silicon inside the ASPEED chip that provides interrupts, programmable interrupts at a certain time period. And it's just a bunch of registers in the ARM address space. And so to model that, you implement a read and a write callback. So when the code running inside the system tries to read from that address space, it falls to this read callback and you return the correct data. Something that is a little bit surprising when you first get to writing QEMU models is that you don't have to be all that accurate with the way it works. I don't have any further insight into how the ASPEED works than the documentation that we all have and the Linux kernel drivers. And that was more than enough to be able to model all the bits and pieces in QEMU that we've got. Every now and then you might bump into a corner case, but for the most part, all you need to do is write enough model such that the kernel driver is tricked into running on, it's tricked into thinking it's running on real hardware, and that's surprisingly minimal in many cases. An example of this is is a temperature sensor. So the TMP105, which lots of OpenBMC systems have in them, has a pretty comprehensive model upstream. But when you have a look at the code, full screen, starting from the bottom, so there's a bunch of callbacks we have here for registering the type information and kind of registering with the QEMU object model, all the bits and pieces that go around. But the most important bits are the RX and TX callbacks. So in RX and TX, we read from an internal buffer and read and write from an internal buffer. And those, because it's an I2C device, those callbacks fall into these read and write callbacks, which, as you can see here, are relatively straightforward. So there's some internal buffer state kept in the model, and when a certain register is read, that data is returned, and it's as simple as that. So that this driver is 270 lines long, but most of the logic is implemented in these two callbacks. Sometimes you might think that that's a little bit too complex. So I'll show you an even more straightforward way to do a model, and that's one that I did for the DPS 310, which was an I2C temperature and pressure sensor. And so if we go into hardware, MISC, here we go. Here's my wonderfully engineered bit of code. So what I did is I used I2C dump to dump out all the registers in the device, and I put them in an array. And so the internal state of the device, as it was when I connected to my Linux machine without a driver, is represented in this array. And so in the reset callback for the device, I put all those values in, and then I've got my read and write callbacks that essentially just return those values. I did implement a little bit of logic in here in that I implemented the reset register. So when the kernel driver tries to reset the device, it calls the internal reset function, which just resets all those values. But apart from that, all that the model is doing is reading the data that gets asked to be read. And when there's a write, it puts that in the buffer. And so potentially a model could be as simple as that. This isn't a model that I submitted upstream. the big huge array of reset values probably wouldn't fly with review, but it wouldn't need that much cleanup to be acceptable for Upstream. I suspect documenting some of these values and making sure that only the ones that are relevant are being included would be sufficient for it to be submitted Upstream. Obviously, here's another thing that I had to do. I had to set some status bits so that the kernel driver would think that the device was ready to return a temperature sensor reading. So yeah, pretty simple here. And as I spoke about before, there's some QEMU objects here that would be able to set through the monitor interface to change the virtual temperature of the device and pressure, because it's a pressure temperature sensor. So yeah, that's a really simple, that was one of the first bits of QEMU code that I wrote. Or maybe it wasn't, but yeah, I wrote that pretty early on the piece, a couple of years ago now, and so kind of hopefully that gives you the confidence to jump in there and write some QEMU code. And so I kind of spoke about that a little bit in my slides here about using I2C dump to create a simple model, and then against that simple model, I wrote the kernel driver and debugged the kernel driver, which was good fun. Is there any questions about developing in QEMU? No? All right, so got a bit of a summary slide here. So what are the next steps in QEMU and OpenBMC land? For everyone who's listening to this talk, I'd like you to jump in there and try to use QEMU to test your next user space change. Whether you're building a full image and booting that, or SCPing the binary for the application that you've modified in there, give that a go. Pick a temperature, pick a sensor that your system has and add an I2C model for it into QEMU and see how that goes. If you can find some bugs in your stack or test some state changes inside your BMC system by doing that. The other big one is we could potentially have more QEMU booting happening in our CI system. This is obviously dependent on CI resources in the terms of compute power, but also someone to maintain it. Because the CI gates everyone's commits, you need to make sure it's always working. But potentially we could add some more to our CI, or we could have at least more screening of the commits that go into OpenBMC that they don't break other systems. As far as the team that I work with goes, we're continually working on the modeling in our spare time. One of the things that I've been looking at recently is doing eMMC boot. So you would have seen on the list that lots of work's been put into building a machine type that boots off of eMMC. And so being able to test that in QEMU is a bit of a priority for me. And so I'm looking at how to model that in QEMU. Again, not model all the exact details of the way that the ASpeed works internally, but model just enough so that it will load in the same way, and so we can test the same code fast. We've also been doing some simple modeling of our FSI bus. So that's an I2C-like bus that IBM uses for test, debug, and monitoring of the host processor. I imagine it's a little bit similar to PECI in some ways. So potentially people that care about PECI could do some of that modeling in QEMU once they finish upstreaming their kernel patches. And the other kind of big picture thing that Cedric in particular has played with is a proof of concept connecting a host QEMU instance to a BMC QEMU instance. So connecting up the virtual UART and the BT interface and pretending to boot an entire system with both the BMC and the host, kind of doing a co-simulation kind of those two. That could be pretty interesting, because at that point you can start testing lots of the host interfaces that your BMC has and getting some confidence there working without a working host system. So you can do that pre-silicon, or you could do that before the board derived or whatnot. The other bit of big news in QEMU OpenBMC land is that Google have been working with Nuvoton to do a model of the POLEG chipset, and so the 730 based machine that's in Upstream OpenBMC, the GSJ, I can't remember what it's called, but one of the machines that's either merged or just about to be merged upstream. So that'll appear in the next revision of QEMU, and that'll be really cool to see. So here's some links. I'm going to reply to the mailing list thread with a copy of these slides, and so you can follow along. Feel free to hit me up on email or on IRC to talk about QEMU, and I can follow up on any questions you have. But thanks for coming along, and I hope you learned something today.
Thanks a lot, Joel. Very informative. Just a quick question. So you mentioned about, like, say, host QEMU and then BMC QEMU.
Yeah.
So did you try like connecting two BMC QEMUs together, like using I2C or any other interface?
Not yet, just because that's not something that I've been involved in.
Okay.
In the same way that you could do the host communication, you could envisage having two BMCs talking to each other. But yeah, that's not something I've tried personally.
Yeah, that's fine. I think I'm thinking, like, say, we can try like IPMI communication, like using I2C and IPMB. If we can try two BMCs talking to each other, or MCTP. A lot of protocols can be developed using this QEMU.
Definitely. And so, like, there's a bunch of ways to break it out, and the easiest way is creating a character device. So QEMU creates a character device on your host, on the machine QEMU is running on, and the second instance talks to that character device and passes data across that. It's not the cases of doing things like that are more around monitoring and control of QEMU, whether that's like in the libvirt kind of KVM sense, or in the sense we were talking about before with temperature sense and whatnot. So there'd be some work involved in like agreeing on a protocol on how to do that kind of extent of communication, but it would definitely be doable with someone to work on it.
So what is the interface you guys are thinking of connecting between host and BMC?
This is just a character device interface. So over the character device, the UART communication would go, and the BT communication also went across there. There's kind of two approaches as well to this idea of simulating with the host. One of them is to connect an actual running host that's running your actual host firmware or host OS stack or whatever. But in some cases, that's pretty hard and doesn't provide that much benefit. The other way to kind of get the benefits of testing is to model, to have some code inside QEMU, have a model that pretends to be the host. So that's the way we did our FSI modeling. We haven't actually connected that to a real FSI host, but we've mocked out enough of the expected interactions that the BMC would have with the host, so that the BMC code could be exercised over that interface. Cedric did a lot of work with this for our host simulation. So nothing to do with OpenBMC or with BMCs, but this was the host, so that we could test the host firmware a little bit more extensively. He had a BMC simulator inside his host QEMU. So that was just another QEMU model that would respond to IPMI transactions in the same way a BMC would, so that the host firmware could be stepped through all the states that it had. So the same approach could be used for the BMC. You could have a host emulator model that would respond to the PECI packets or the IPMI packets or the whatever interactions you're trying to have, and the code on the BMC would do its thing.
Okay, great, thank you.
Joel, another question, like, have you seen any timing issues since this QEMU runs under a different speed than the actual hardware? Have you seen any timing issue that is like, it works fine on QEMU, but not on the actual hardware?
Yeah, we have. So QEMU is not a cycle-accurate emulator in that it just uses the wall clock time of your host machine. So a second inside QEMU will be a second on your host. And so if you're trying to simulate a clock that fires at 24 megahertz or some really high speed, that's hard. There's not enough cycles on the host to emulate the code running inside the machine. And so we have had a few bugs over the years, because essentially what you have to emulate is potentially not every single interrupt that the guest should see is seen by QEMU. but we've worked, Andrew did lots of work here, and Cedric and I actually, we've worked through most of the issues, I think, and so it's close enough. But yeah, certainly if you have something that requires really accurate timing, and particularly, you know, with respect to interrupts and whatnot, you might see different behavior inside QEMU versus the host. And it matters, you know, how fast your host machine is. If I had a faster laptop, it would have been booting quicker earlier. So that's also a concern.
Oh, okay, thank you. Any other questions? Thank you. Thanks, Joel. It's pretty awesome. Yeah.
Thanks, everyone. Thanks
Thanks
very much for organizing these. It's been excellent.
Sure. Thank you.
See ya.
Good night, and yeah, good day. Bye.